Okay, well, hi everyone. Well, I'm Irina Rish. I'm a professor at the University of Montreal and a core member of Mila Quebec AI Institute. And today I'd like to give an overview of work in related areas to a very hot topic these days that many of you, I guess, aware of, is large-scale or so-called foundation models. And the topics include trying to understand how those models actually scale, what the scaling laws for them would be so you can predict their kind of behavior, what kind of unexpected behaviors may emerge at scale, and finally, the last but not least, what do we do about making those models kind of more available to a wider set of people so that basically people can develop those models and analyze them, test them, build on top of them in an easier way that it would be if we only had to work with currently available kind of closed models coming from companies like, well, OpenAI, Anthropic, and Google, because those models, while being state-of-art, they unfortunately are not available publicly, and therefore there is a whole recent movement on open source large-scale AI models that I will be talking about that's trying to kind of correct that situation. Well, all these efforts towards kind of better and better, more capable models are in the whole framework that can be called holy grail of artificial intelligence field. Essentially, people were talking about AGI or artificial general intelligence for quite a few years, but only very recently it's becoming kind of the topic that is much more practical and perhaps even within our reach. Of course, the definition of artificial general intelligence depends on whom you ask and varies from person to person. So there are like debates, and that's why this picture here. But what I mean by that is a bit more practical. It's not necessarily a conscious machine or machine that has all the aspects of human intelligence, but rather it's a system, or maybe it's a collection of systems that is capable of what we would call like a versatile, general, or multitask type of intelligence, something that humans do kind of exceptionally well, even though each task might not be at the kind of world champion level, but nevertheless are very flexible, adaptable, and can do and learn during our life continually many things. AI systems until recently were more of a narrow specialists. That's why actually we were calling it narrow AI. And while they could be world-class chess players or Go players or specialized, I don't know, for detecting abnormalities in X-ray, it would not be so easy to adapt those kind of specialized models to do very different tasks. So the goal was always to try to approximate that ability of humans to be so versatile and broad. And in a sense, we can just adopt the, well, high level, not very maybe formal and precise, but still kind of working definition that OpenAI gave to what they mean by artificial general intelligence, I guess with a focus on the word general. So it's highly autonomous systems that can, I guess, perform as well as or outperform humans at most economically valuable work. So essentially they're multitasking and those tasks are useful. And the whole history of machine learning or even statistics starting from like mid of the last century and more recently all the advances in deep learning, essentially if you think about that, it was always about trying to reach the ultimate goal of generalization. When you train your systems on certain sets of data, and then you can use them for different type of data and tasks, and the different becomes further and further away from what you train it on. Of course, original classical machine learning was assuming that here is a data set which is coming from the same distribution of just images of certain times, say cats versus dogs, and we train a classifier that can generalize to new images of cats and dogs. It's generalization, but quite narrow. So we want to go out of distribution, and then the field was trying to come up with methods and algorithms that would potentially work well out of distribution when the types of images, for example, are quite different, but still there is something in common with the previous domain. But it's not the same distribution of the images, say, you saw before. Similar goals were kind of driving domains, driving the areas with various names, but essentially the same goal, like domain adaptation. You train on one domain, you wanted to work on another domain with maybe minimal changes. Meta learning, try to train on multiple data sets and tasks and hope that in the future you can adapt your model very quickly to some new data and new tasks. Transfer learning, continual learning, doing the same thing sequentially when the data are not available at the same time, but will come to you continually. Bottom line, it's all about generalization, just further and further away, more general. Continual learning, for example, one of the core topics of the research in my group, and also very practical and very exciting topic, is motivated by situations where your agent will have to be adapting quickly, maybe in real time, to novel environments. For example, you can imagine a robot that is doing certain tasks in one type of room, moving to different environment, moving outside, and it will have to be able to learn new things quickly without forgetting what it learned before. Examples keep going on. You can think about the conversational agents like chatbots. You can think that they definitely should be able to adapt to different users. They should adapt to different situations during the user's kind of life, even during the day. And they should be able to hopefully incorporate the new information they adapt to without, again, forgetting what they learned before. Examples go on and on. Just the third one is very kind of typical for applications, say in healthcare, when you train your models on, say, medical imaging in particular kind of set of patients in particular hospitals, and you wanted to generalize and work well later on when you move the model to, say, another hospital, another equipment, another set of people. There are clearly commonalities, and you want your model to be able to extract those invariant common kind of properties and patterns while leaving outside some spuriously correlated features and not to latch on them. So all these kind of examples is where this generalization out of distribution, in this case in continual setting, is very important. And just kind of to give the bit more formal definition of what it is, it's a setting that's more challenging than usual machine learning, because in standard machine learning on the left, you would have a training data, say your cats versus dogs. You will have your model, say deep network, and it has to train to learn that function that maps image to the label, so that when at the test time it will see new images of cats or dogs, it has to label them correctly. Much more kind of challenging situation is what I was giving examples for, the continual learning, where your tasks and data will be changing over time, and you will have to switch to classification of different type of objects, and perhaps even to different modalities if you push the continual learning even further. And your model need to keep learning, say your deep network has to keep adapting its weights. And the trick here is that when it does it, it can adapt to the new data. It has to make sure it still can work well on the old data and old tasks. So it's this generic kind of challenge of transfer versus interference, or also called stability versus plasticity, when the model sharing weights across all these different tasks and data sets has to be able to transfer its knowledge back in the past, not to forget what it learned, and in the future. The more it learns, the easier it should be for it to learn in the future. So this is kind of one of interesting areas of research that we were focusing on. And as I was just saying before, it also connects to all the subfields of machine learning that were really popular in the past decade and even earlier. It's all about generalization. And most recently, as many of you have seen, we kind of witnessed this explosion of so-called foundation models, or large-scale, pre-trained in unsupervised way models that seem to be having this property of generalizing often really well from out of distribution to kind of from very small number of new examples to totally new data and new tasks. So they are few shot learners. And the interesting observation here is how come, like, we had all this kind of complicated sometimes and sophisticated algorithms and specific models trying to get at this holy grail of generalization, while scaling the models and scaling the data on which we pre-train them seems to be getting there, well, almost effortlessly. So it's not something that we haven't observed before, and I just kind of wanted to remind the so-called bitter lesson many of you have seen also probably by Rich Sutton. It was just like a very brief but very influential article, basically making the point that if you look at the whole history of the AI research in the past decades, people start with complicated methods, putting lots of expert knowledge, writing maybe rule-based expert systems, and they do not withstand the test of time, because later on, with more compute and data, more generic methods that are scaled outperform those very specific ones, and usually by large margin. So essentially, that the idea of the bitter lesson kind of paper is to think about looking in the future, what methods will stand the test of time, and perhaps simpler generic search and architectures like, well, transformers, for example, quite generic without any specifics of, say, convnets and so on, at scale may actually do the job just as well, and that's what people will be using in the future. So why is it important? It's just kind of from both philosophical and practical perspective. If scale has such a huge impact on what's going to be used in the future, you may be careful about deciding what you spend your research time on. And essentially, the point is that if you could predict earlier that certain generic methods just with enough compute and data would scale and outperform more specific methods, then probably you wouldn't have to invest too much time and development of those specialized methods that only would work for you now but will not be used in the future. And examples go on and on with classical things like playing chess, where initial programs were very detailed, kind of programmed in hard-coded rules and hints and heuristics. Later on, you essentially have just massive deep search, and at large scale with larger compute, it just kind of works. Similar things with Go and so on and so forth. So that's kind of higher level idea of what is also seem to be happening right now with large scale models that used scale of the compute and data and relatively simple, without too many maybe inductive biases type of architecture of transformer to get to the problem of generalization and effectively in many cases solve it without going into too sophisticated methodology. So the lesson here is that while we may want AI agents that are quite capable, we rather would like them to be able to discover like we can, rather necessarily contain the results of what we discovered. So we don't necessarily have to put in them expert knowledge, but we want to make them so that they are able to build it. And Recently, yes, as I said, we're all witnessing this explosion of large-scale models and also applications of those, starting from 2020 GPT-3 and multimodal models that followed that, GPT-4, now ChatGPT that is kind of extensively used by so many people for so many applications right now. So it's really like a explosion in the field, so to speak. So it's all based on the properties of these large-scale models that essentially getting to the holy grail of machine learning, that out of distribution generalization. And another word for them, as I mentioned, is like foundation models. The term was coined by the Stanford paper in August 2021 that essentially captures the property of this large-scale model. So the idea is that, yes, you train model on huge amounts of data and you train it in unsupervised ways. So essentially you capture patterns, you capture the distribution of data without specifically trying to train it for any particular task. And those models can be later on adapted, fine-tuned to specific tasks. So they serve as foundation for kind of future applications, and they kind of essentially as foundations, they're incomplete. You need to build on top of that. So that's why foundation models. And the list is highly incomplete. It's just showing a bit of history, which all of you know. And currently there is what people call Cambrian explosion of not just language models, but also multimodal models of this type, from GPT-3 to CLIP in 2021 to DALL-E to Copilot for code generation, and then last year Stable Diffusion and ChatGPT, and so on and so forth. So what are those models really doing, and why they are like unsupervised and pre-trained? As I said, they're basically just trying to capture the distribution, the underlying distribution of the data, say in this case language. So GPT-3 or any of this type of, say, models in this class essentially are autoregressive models. They're trying to accurately learn from diverse and large amount of data the distribution of, say, next token given the window of the previously seen tokens, and in more modern systems that window expands, you have like longer and longer kind of context. But what really made the difference between, say, GPT-3 and GPT-2, architecture is essentially the same, and objective function is essentially the same, and training is essentially the same. The only big change was a scale by orders of magnitude between the previous models and, say, GPT-3. Well, by now, of course, GPT-3 is no state of art anymore, and we have GPT-4 and the whole family of language models, both proprietary and open source. I'll talk about that later. But essentially, yeah, so that's example where more is not just more is different. In terms of number of parameters, going orders of magnitude larger, in terms of training data as well. And as I said, examples go on and on, but remember the holy grail of machine learning being out of distribution generalization. And here we go, without any sophisticated, specifically designed algorithms or model details to achieve that, you simply have say, that's example of CLIP model from a few years ago, when the kind of famous CLIP paper showed that the model generalizes to very different type of images, and there's a classification there much more accurately, basically generalizing out of distribution, zero shot, than the state-of-the-art like ImageNet trained ResNet model. So the scale kind of really helps you to get out of distribution, seems like. This is kind of a classical plot showing how the performance of these models, in this case GPT-3, it's from the original GPT-3 paper, how it scales with the number of parameters. And basically you can see on x-axis the data amount grows, and larger models are able to exploit this increase in the data much better, with a huge kind of gap in the performance. So going going 2 orders of magnitude in model size essentially gives you huge improvement in the performance measured by accuracy here. And then, of course, talking about scaling laws, the question was, can we understand and predict what happens at scale? So there was a seminal paper by Jared Kaplan with collaborators from OpenAI back then, where essentially empirically they established that whenever you increase amount of, so the key parameters would be like amount of compute available, the amount of data, and the number of parameters. And these 3 key variables are all leading to very interesting kind of prediction of how their performance, in this case test loss, improves, the loss decreases with increase in those variables. Say if you set compute to particular value and you are not constrained by what size of the model you choose, you can try different sizes and how much data you give to it, you are not bottlenecked by the 2 out of 3 variables, then the performance will be following what's called power law, which is essentially straight line when you plot the results on log-log scale. So essentially it is, it's called power law because essentially it's like a polynomial with particular power, as you can see here. And the interesting thing that this power law behavior happens when you, for example, increase data set size while compute and parameters are kind of not bottlenecked. And similarly, just with different kind of exponent in the power law, you get the dependence for parameters. So it's quite beautiful and simple because essentially it gives you a tool to predict what will happen when you increase the scale of your model or the data, or you have more compute available. And why it's important to study scaling laws is because unlike the traditional machine learning evaluation of different architectures or different algorithms where you would compare them on fixed size data sets, if you see, for example, the whole trend, like here it was a classical example from the vision transformer paper, where they show that when the data are relatively limited, like 10 million, convolutional networks, as it was a state of art at that time, indeed outperform vision transformers. But the situation will reverse when more and more data become available. So if you're looking into future with more compute and more data, you know that maybe you should invest your attention and resources into, say, vision transformers, more generic model without any specific, say, convolutional structure. And interestingly, I mean, this history of scaling laws, which one can view as investment tool for machine learning, as I call it, it goes back a few decades in machine learning field. Actually, the very first paper that we could find that would look into the scaling laws of performance as kind of data or compute or number of parameter change was a paper from New Rips 1994 by Karina Cortes and her famous co-authors, including Vladimir Vapnik. So essentially, they also were looking into the power law equation and trying to predict performance of their models also at much smaller scale. And their kind of famous picture was making same argument as I made with vision transformers versus convnets. So that was like a hypothetical setting where they said, well, imagine that at small data set size, you compare your methods and conclude that one is better than another without knowing how things would scale. You may make a wrong conclusion because at scale, the situation will reverse. Therefore, you should be comparing methods, architectures, algorithms, looking at the whole scaling law plot rather than at the point comparison. So that was kind of their motivation too, and they did see power laws in increasing kind of amount of data. And then more and more people were looking into that more recently, 2017. Basically, the paper by Joel Hasnes showed, and co-authors, that you see power laws also with increasing data set size, Then other papers more kind of recently essentially were observing similar kind of performance with number of parameters. And then essentially Jared Kaplan added the third variable, compute, and also showed power loss in the picture that I showed before. So this was great until people started observing that performance may sometimes increase in unpredictable or abrupt ways. And this is a picture from the original GPT-3 paper where they tried it on particular task of arithmetic, like 2-digit, 3, 4, 5. The more digit kind of addition and subtraction you use, the harder is the problem. And essentially what that plot was showing that until certain size models were unable to really do that and only started improving performance abruptly at certain scale. So this was interesting, and then even more interesting examples came into picture. This is so-called grokking paper, where people observed that when you increase the compute kind of for fixed model and particular like data set size, you keep training the model, it's not performing well until certain point where it suddenly improves performance on training data, it groks it, that's why the name grokking, and then soon or relatively soon after that, same grokking happens for the test error. So all these kind of unusual abrupt changes were later on observed when people were just kind of trying to see what happens on different other problems with other models. And the emergent abilities of large language models was a paper from Stanford where they showed multiple empirical examples of this type of nonlinear changes in their performance with scale. At this scale, in this case, it was model scale. With grokking, it was compute scale, and people also observed with data scale. So that motivated us basically last year to do this work, primarily led by my student, Ethan Caballero, to come up with maybe more generic framework to try to find a functional form for neural scaling laws that would capture all of these behaviors, basically one scaling law to rule them all. And essentially, I will not go into all the details. You're welcome to look at the paper. It was just presented at ICLR in Kigali, Rwanda, basically last week. So it's a more generic form that includes those power laws as particular cases, but it's very flexible. It essentially can capture behavior that have different regimes of power law scaling connected to each other at either sharp or smooth kind of breakpoints. And so far, we were able to essentially not just fit, but extrapolate, predict behavior of various large-scale models in various modalities, even if that behavior would be non-monotonic like here, or it would have this kind of transitions. We were able to predict it even like before the transition happens, well, provided that it was either close enough or we had enough sample points to make the prediction. This was kind of quite impressive, mainly because not just that it able to extrapolate accurately, but the sheer range of models, problems, and modalities that all could be predicted using this generic broken neural scaling laws. That was quite impressive because here you see that we were able to predict both performance downstream, upstream, vision language, audio, video, diffusion models, so on and so forth. Basically, whatever people were presenting as scaling results for their models in recent papers, we were able to capture with this functional form. So it indeed seems to be quite universal. Anyway, so I really invite you to look at the paper for more details. But I want to move on and now switch to the last third part of kind of my talk. Essentially, what we're observing with large-scale models, right? Back to the bitter lesson that general methods that leverage computation are ultimately the most effective. But you need computation, you need compute that you can leverage. And currently, we see that state-of-art was mainly produced by companies like OpenAI and Anthropic and Google. And yes, indeed, as Greg Brockman was saying, we think most benefits will go to whoever has the biggest computer, so you can scale the most. So what do we do if we are in academia or we're trying to do like kind of open source communities and so on to reproduce those results? Well, there are different ways to go. And in our case, we kind of teamed up with researchers from several universities, open source communities, and this is international collaboration that keeps growing. Essentially, besides University of Montreal and Mila, we teamed up with Lion and the Jülich Supercomputing Center, EleutherAI, and also expanding it to more collaborators, AI Sweden, and so on and so forth. Not everyone currently is shown there. The most recent expansion was to include also our collaborators from Stanford Center for Foundation Models and Together company. And we just recently completed training and released the open version of Llama called Red Pajama Inside, which is trained on the Summit supercomputer. It's kind of specification of several supercomputers, because we decided that perhaps with this type of collaborations, we can try to apply for large compute at government supercomputers. Summit is one of them. In different countries, there are somewhat smaller, but also quite powerful ones like Jewels in Jülich Center, big Genzei in France that Big Science is using, so on and so forth. So with help of that compute that we got as part of our Insight proposal, we were able to like start training those medium-sized models, of course, not the GPT-4 level, but still quite comparable to, say, the recently released Llama by Meta. Unlike that Llama, our Llama is with Apache licenses, and it's fully available, fully open. You can build on top of that, and I think that's a very interesting trend, like a explosion of this open source models in the past few years. So this is the project that I was mentioning. Essentially, there is so-called program at Oak Ridge facility that hosts Summit Supercomputer. It's called Insight. And last year, we applied together with Eleuther, Lion, and other collaborators to essentially build scalable foundation models. And there are multiple other, as I said, collaborators from different universities and organizations. So this is essentially the project that tries to both build from scratch and also fine-tune both language models and multimodal models. I'm not going into too much detail. As I said, work is in progress, but the first kind of the model that was already trained during the months of April is this Red Pajama, for the name of the data set, dash Insight model that I mentioned. So fully open reproduction of the Meta's Llama. And with this kind of collaboration, what is our goal? And collaboration is international and constantly expanding. Essentially, we're aiming to build open source, well, not necessarily maybe equivalents, but pretty good open source language models, multimodal models, expand it to other kind of ways of training, like continually, as I was mentioning, continual learning type of settings, and also maybe transfer them to new domains that they were not trained before. So the idea is that we really would like, we believe that democratization of AI, making it open source and available to like much wider population, is probably a better way to go, not just for the kind of number of applications that you can build on top of them, but also in terms of safety, because the models are transparent, they're open source, open parameters, open data sets, and this transparency can allow multiple groups to test those models for all kind of potential unexpected behaviors and see what data go into them. So this transparency, unlike closed models currently available from industry, such as, for example, ChatGPT, I think can potentially be even a safer road to a more useful AI. So I know that's somewhat controversial topic, but I think there are many arguments kind of towards AI democratization and open source as a better alternative to the closed models at only a small number of companies that have that large compute in their possession. At this point, I think I will conclude and I'll take questions if there are any. Thank you very much. Thank you so much. Yeah, thank you for inviting.